The construction industry extracts a massive physical toll from its workforce. Constant heavy lifting and awkward, repetitive postures put builders at an exceptionally high risk for work-related musculoskeletal disorders, chronic pain that can shorten careers and degrade quality of life. Look closely at the movements of a bricklayer. Every time they reach down to scoop mortar or lift a block, the entire weight of their upper body, plus the material, levers directly against their lower spine. For years, engineers have pitched a sci-fi solution to this ancient problem: passive back support exoskeletons. The idea is to wear a mechanical frame that absorbs the gravitational pull of bending forward, relieving the stress on the human skeleton. Take the Levo V2.57, the commercial exoskeleton used in a recent Danish field study. It uses an anterior chest pad connected by rigid bars to spring-loaded smart joints at the hips. When the wearer bends forward, the springs compress, generating an upward push against the chest to counter the downward weight. On paper, the physics make perfect sense. But when researchers finally strapped these advanced suits onto real professional bricklayers working on active job sites, the results completely defied the engineering theory. The suits actually increased the physical strain on the workers. The problem with early exoskeleton research is that it almost entirely took place in pristine, controlled laboratories. Test subjects performed isolated, highly standardized lifting tasks that looked nothing like actual construction work. To find out what happens in practice, researchers in Denmark took the experiment directly to chaotic, real-world construction sites. They set up a randomized crossover study, meaning the masons acted as their own baselines, building actual walls both with and without the mechanical suits. They wired 18 professional bricklayers with SEMG electrodes on their skin to measure muscle signals. Alongside these, 17 inertial measurement units mapped full-body kinematics, feeding a live 3D motion-tracking skeleton to a laptop on the scaffolding to capture every exact angle. By forcing the technology out of the lab, the researchers subjected these idealized designs to a brutal stress test against the unpredictable, highly dynamic reality of human labor. To understand exactly why the suit failed, we have to look at the underlying geometry of human movement. This animation shows a person moving purely in the sagittal plane. That means simple, straight forward and back bending. This is the predictable motion found on a standardized assembly line. Exoskeletons excel here. Because the movement is linear, the rigid structures easily absorb the load, but masonry is entirely unstandardized. Bricklayers have to grab materials of varying weights from different heights and apply them to complex surfaces. Watch how this wireframe moves during a real bricklaying task. The mason operates across all three planes of motion simultaneously. They bend forward in the sagittal plane, reach sideways in the frontal plane, and rotate their trunks in the transverse plane to set the brick. This created a severe, inescapable mechanical conflict. The exoskeleton is built with stiff vertical bars, intended to guide the body straight down and straight up. As the masons naturally twisted and leaned sideways, they had to actively fight against the physical resistance of the suit itself. Far from acting as a supportive aid, the rigid technology functioned as a two-dimensional straitjacket forced onto a three-dimensional job. The electromyography data reveals exactly how much that biomechanical clash cost the workers physically. The researchers zeroed in on the erector spinae, the long muscle bundles running down the lower back. These are the exact muscles the exoskeleton was engineered to protect. This chart compares the worker's baseline muscle strain against the strain recorded while wearing the suit. Instead of a drop in effort, the data shows a 5.2% increase in muscular activity in the lower back during exoskeleton use. The workers' muscles were engaged in a two-front war. They still had to lift the heavy bricks and mortar, but now they also had to exert extra muscular force just to overpower the stiff spring tension of the exoskeleton whenever they needed to rotate. While the suit successfully offset gravity during a perfect forward bend, it generated a constant, unnatural friction against the workers' bodies every single time they performed their actual craft. The biological data proved the suit was physically taxing, but the researchers also wanted to know how it impacted the daily workflow. Through detailed usability questionnaires, the masons reported that the chest pads caused uncomfortable pressure, and the rigid frame directly interfered with their ability to maneuver quickly and efficiently on the scaffolding. This graphic breaks down the final consensus on adoption. Out of the 18 masons who tested the suit, only 4, just 22%, said they would be willing to use the exoskeleton in their daily work. The researchers defined this failure precisely. It is what happens when technology misaligns with work demands. The tech industry routinely attempts to solve complex occupational hazards by engineering isolated solutions. But you cannot apply static, single-plane mechanics to dynamic, multiplanar trades and expect the human body to just adapt. If we want to genuinely protect workers and improve occupational health, engineers have to leave the idealized physics of the laboratory behind and design tools that respect the